In this video, I am going to talk about the impact of the boiler exit temperature on performance of boiler. This is a new video on the playlist on analytical approach in boiler O&M. You are watching the official YouTube channel of indiaboiler.com, that is Boiler Analyst, and I'm Anshuman Sen Sharma. Now, as I have discussed in my previous videos, an analytical approach is basically a logical step-by-step approach towards understanding any performance or reliability related factors that affects the boiler system. Now, the first thing, when you look at the chimney of the power plant, from where the boiler stack gas is coming out, what you should actually see is money is coming out of that chimney, right? That is the way to look at the performance. You have to convert everything in terms of the monetary loss, and then you understand that what kind of effort you should give to control that. Now, when I'm trying to understand the impact of various boilers parameters on boiler performance, so analytically thinking, we need to understand, okay, what are the losses? So let us first look at the boiler losses. The first one is the dry gas loss through stack, right? Usually calculated with the formula of mg is AP Tg minus Ta. In this, mg is the mass of dry flue gas that can be calculated if you have the ultimate analysis, and the excess air, that is the O2 percentage measured in the APH inlet, right? And the APH outlet gas temperature as well as the ambient temperature. So mg is the dry gas mass, Cp is the specific heat of flue gas, which is considered to be 0.24 kilocalorie per kg degree centigrade. Tg is the APH outlet gas temperature, that is the boiler exit temperature, and Ta is the ambient temperature, right? The next three losses are of moisture loss. First is the moisture resulting from the combustion of hydrogen, that can be calculated as this 9H into 584 plus 0.45 into Tg minus Ta. In this case, H is the mass of hydrogen in 1 kg of fuel. That can be calculated from the ultimate analysis, and in fact, if you do not have the ultimate analysis, it can be calculated from the proximate analysis also. May not be very accurate, but good enough for us to understand the performance criteria, right? 584 is the latent heat, 0.45 is the specific heat of steam at the condition of combustion, and again Tg is the APH outlet gas temperature, Ta is the ambient temperature. The next moisture loss is the moisture loss due to the moisture present in the fuel, right? So in this case, Mw is the mass of moisture in kg per kg of fuel, and the remaining is the latent heat and the superheat that is going away with the steam when it passes through the flue gas from the stack. The third loss is the moisture in the atmospheric air, that is combustion air we are using, that can be calculated as the Ms into FH. Ma is the total air that we are using, that is the total sum of primary air as well as secondary air. FH is the factor of humidity that can be found out if we have the psychrometry chart, air psychrometry chart, and the dry bulb temperature as well as the well bulb temperature, right? Again, Tg minus Ta is the APH outlet gas temperature and ambient temperature, right? Next loss is the incomplete combustion loss, that is for the loss contributed by the CO formation, right? So in this case, we need to measure both CO and CO2 in the flue gas, and it can be calculated as the ratio of CO percentage to the total of CO plus CO2 percentage multiplied by C, that is carbon in 1 kg of fuel, right, into 5654, that will be the heat taken away as a result of incomplete combustion. The Sixth loss is the unburnt losses. Unburned in the ash, it can be unburned in the fly ash as well as bottom ash if we talk about a solid fuel fired boiler where it can be calculated. And considering the fly ash and bottom ash percentage as 80-20, it can be calculated as ms. Ash is the mass of ash per kg of fuel. 0.8 is the 80% of fly ash contribution multiplied by the unburnt percentage in the fly ash plus 0.2 is the percentage contributed by the bottom ash multiplied by unburnt percentage in the bottom ash, total multiplied by 100 because we are talking about percentage, into 8084 kilocalorie, which is basically the heat value of carbon, unburnt carbon, right? Then we can calculate the sensible heat loss due to fly ash, because the fly ash going at a high temperature, right? So at APH outlet, the temperature of the fly ash should be same as the APH outlet gas temperature. So 0.8, again the 80% of the ash is going as fly ash, assuming that will be the mass of ash per kg of fuel multiplied by 0.8 into Cp of ash is taken as 0.2 kilocalorie per kg degree centigrade, and it is coming in as ambient temperature going as APH outlet gas temperature, so Tg minus Ta mc delta T, right? And you can also calculate the usually we do not, but we can calculate the sensible heat loss due to bottom ash, right? So in this 20% of the ash is bottom ash multiplied by 0.2 is the Cp. If you are having the bottom ash temperature measurement, then that will be the T ash minus T ambient. The other losses, that is basically the convection radiation losses, usually we do not calculate because it involves a lot of parameters to calculate it accurately. So we take a standard, usually the standard given by ABMA, that is the American Boiler Manufacturer Association, and for power plant boiler it is taken as 0.4%. Now if I take a look at all these losses, the first thing you understand that which parameter is appearing in these losses the most number of times, and that is the APH outlet gas temperature Tg. So it affects 5 of the 9 calculated losses, right? So if we are talking about a parameter that affects the performance of the boiler, the most significant parameter, naturally it has to be the APH outlet gas temperature, exit temperature, right? Now, thing is that in my experience, I have seen most of the systems, majority of the systems where I have gone to do some assessment or some troubleshooting, I have seen that the APH outlet gas temperatures are usually on the higher side, right? Not much, priority is given to that particular parameter. They are worried about the unburnt, many places they are worried about the unburnt losses, right? They are worried about, sometimes they are worried about unburnt in the bottom ash, which actually contributes very little to the total losses, right? But not sufficient amount of importance is given on this particular parameter. The first thing is the assessment of exit temperature, right? In most cases, when you understand that your APH outlet temperature is high, then when you compare it with some standard temperature which is possible in your system. So one temperature is the design temperature, which will be available in the technical manual or the whatever the promised parameter given by your OEM from there. But I believe the better one to compare is the parameter which has been recorded at the time of the PG test, right? So PG test parameter should be always as a comparison parameter to understand whether our boiler exit temperature is going on the upper side or not. Because believe me, if it goes by even 4 or 5 degrees centigrade, right, it is really worth looking to the reasons why it is going up, and if we can correct it, it can save crores of rupees in terms of performance. Okay. Now, the corrected gas temperature is the first thing we need to look at, because most of the times I have seen that people are happy with their temperature because they have shown that sir, our design temperature is this and our actual temperature is very near to that. The first thing is that whether the temperature which you are measuring is the corrected gas temperature, considering there is an APH liquid. If there is an APH leakage, and particularly if it is a rotary air preheater, then there will definitely be leakage, right? Somewhere less, somewhere very high. And that temperature is going to mask the gas temperature, because cold air is getting mixed with the hot gas, and the resultant temperature is seen in the DCS, right? So the corrected gas temperature is the first thing which should be compared. When we are monitoring the gas temperature, it should be the corrected gas temperature. Now there is a calculation by which we can calculate the corrected gas temperature. You can put it in an Excel sheet, so that anytime you put the necessary data, for in this case TG out is basically the APH outlet gas temperature. AL is again the air leakage as a result of APH leakage, that can be calculated by this formula, is O2 out minus O2 in by 21 minus O2 out into 0.9 is an empirical formula. So what we need to measure, we need to measure O2 percentage at APH inlet, which is always measured in every boiler, but O2 out is another very important parameter to measure, particularly if you are having an RAPH. In fact, I have seen a number of boilers where even a tubular air preheater is having a O2 percentage difference of around 2-3% at inlet and outlet. So much leakage can happen from there also, right? Particularly due to corrosion. If you are having sulfur in your fuel, then it's likely to have a lot of leakages. Now, when you have the AL, so you have to have the air temperature, ambient air temperature, right? So you can always check the corrected gas temperature as TG out plus AL into CPA is the specific heat of air, which can be taken as 0.23 kilocalorie per kg degree centigrade, into TG out minus T air in divided by CPG, that is the specific heat of flue gas. As I told you, it can be taken as 0.24 kilocalorie per kg degree centigrade, right? And into 100, if you are taking a percentage, you don't have to multiply the divided by 100 if you are taking only as a fraction, like I have taken in the bottom as AL is a fraction, air leakage as a fraction. Okay, so I'll give you an example. Suppose very recently I have seen a system, right, and they are worried about the unburnt, huge amount of unburnt. And when I check their flue gas system, air and gas system in their DCS, I found few things. One is that the gas temperature was coming to reasonably good, as good as their design temperature. But what about the leakage factor? So if you see the inlet and outlet O2, the inlet O2 was coming to 4.25%. Outlet O2 they have been measuring, good thing about them is 6.83%, right? So that gives you, using that AL formula, air leakage formula, that gives you an air leakage of around 0.164, that is 16.4%. And mind you, this was a tubular air preheater. Yes, if it is an RAPH, rotary air preheater, I can understand 10 to 11% is a design leakage, right? If it is exceeding 15% leakage, then even for RAPH, it is a factor which should be looked into. But for a tubular air preheater, this is pretty serious, 16.4% leakages. And if you take that into account, the corrected gas temperature is instead of 133.2 degree, it is coming to 149.42 degrees centigrade, right? Now that is the impact of these leakages, straight 16 degree centigrade increase in the gas temperature. Now, if you are looking at the DCS, you are pretty much used to that gas temperature, and it is not going to bother you. But if you have a monitoring system where the corrected gas temperature is always in front of you, right, then you get a better understanding whether our APH outlet temperature is in increasing format or not. Now, talking about monitoring this, again, various factors in boiler system affects the gas temperature. For example, load is one, how much air you are using, what quality of fuel you are using, particularly if you are a coal-fired boiler, right? So, I will share one method of monitoring this, which I usually apply in wherever I go for optimization of a performance system. Uh, I'm going to share this with you, how to monitor this APH outlet gas temperature from historical data. Now, the first thing what you can do is you can take the record of the historical data from your DCS pi data, right? Make an Excel sheet. Now, make an Excel sheet, take the load, the gas temperature, right? The air flow, that is the total air flow. You can take PA plus SA flow, and the fuel flow, right? Now, because when all this fuel flow, air flow, load are in similar range, then the gas temperature is a comparable gas temperature. That is going to give you a comparison, right? So what you do is put it in an Excel sheet and then use a filter. Use a filter giving a plus minus of depending upon the capacity of your system, right? I usually go for 500 megawatt. I go for plus minus 5 megawatt for load, plus minus 5 ton per hour for both air and fuel flow, right? And then you record the timestamp for which is coming within that filter region of the data, right? And then compare. And when you compare, put again in another Excel sheet where along with the load, fuel flow, air flow, you also have the O2 in, O2 out, and make another column where you can calculate the corrected gas temperature. And as a comparison, you can take the design temperature or the temperature which was recorded at the time of BG test. If you monitor your APH outlet temperature this way, then you will understand whether you actually have a problem or not, and then you conclude, right? Then your conclusion should come. So this is the way one can monitor the APH outlet gas temperature, and I'll tell you, if you do that, in most cases you are going to find that your APH outlet air temperature is 14, 15, 20, 25 degree more than what it could have been, right? And a serious attempt should be taken to correct that. Now, how to analyze that? What is the factor that ultimately is leading to this increase in the gas temperature is again a very detailed discussion, which I can try to cover in another video, how to analytically, approach to identify what is the cause that is leading to APH outlet gas temperature increase. So with that, I'm concluding the session. Thank you very much. See you soon.